In the reading assignment and in lectures, you saw how when you are given some irrotational field F and you're told that its divergence is equal to some charge density rho, charge density, and this would be the vector field produced by this charge density, field produced. You saw how to use divergence theorem to get from this point form to this integral expression, where on the left-hand side, you would have outward flux of the vector field through the surface S equal to, on the right-hand side, to the total charge enclosed inside of the surface. In section 3.3, the problems involved were spherically symmetric, and the charge density was only a function of the distance from the origin. So it didn't depend on the phi, and it didn't depend on theta. As a result of this, the vector field produced is going to be a function, is going to be in the radial direction, and its magnitude is only going to be a function of the distance from the origin. So here I sketched f, which is equal to some function of the distance from the origin times r hat. Now, if f of r is negative, then the field is going to be converging on this sphere that I've shown here. Gaussian surfaces, which is this surface S here, that are good for this kind of problems would be spheres. And the reason they are good choice for this kind of problems is that the vector field F is parallel to the normal vector of the surface. And also, the magnitude of this field is constant everywhere on this surface. So the flux integral calculation on the left-hand side becomes much simpler. Let me show you. You have the left-hand side of the divergence theorem. Then here I plugged in the expression for f, and I plugged in, instead of generic r, I plugged in the r on the surface, so the radius of the sphere. And then we have r hat dotted with the surface element of this sphere. Now, f of rs is just a constant, so it comes out of the integral. And you're left with this integral here. Now, r hat and ds go in the same direction, right? So n hat is in this direction, so ds is also in this same direction. Which means that when I take a dot product between ds and r hat, I get the magnitude of ds. Let me explain why this happens. We know that r hat dotted with ds is equal to magnitude of r hat, which is 1, multiplied by magnitude of ds, which is just scalar ds, times the cosine of the angle between them. But if they are parallel, then the angle between them is 0, so this cosine is 1, so we just end up with ds. So this expression is just ds. So we get this here. Now, this integral is just the surface area of the sphere, which is equal to 4 pi r squared. Now, what's really important is that none of this would have been possible, none of these simplifications would be possible if the sphere, if the Gaussian surface didn't respect the symmetry of the problem. If either the problem wasn't spherically symmetric, or instead of the sphere, I chose a cube or some other kind of surface. Here's the steps where it's really important. You see how here I was able to take f of rs out of the integral? I could only do this because f is a function of the distance from the origin, which is constant on the surface of the sphere. Now, if f was a function of phi and theta, it would have to stay inside the integral. Also, here I used the fact that r hat and ds are parallel, which is the case because of the way I chose the surface. Now, this integration here is a shortcut, and it's probably not how you're used to doing this. You're more used to parameterizing the surface and performing the integration this way. So I will show you, in case you're curious, how it would look like. You would parameterize the surface in terms of phi and theta, giving you this expression here. Then you would compute t phi and t theta and take a cross product, which gives you this. I'm going to factor out rs squared sine phi. You'll see later why. It's just to see some things more clearly. We will get sine phi cos theta, sine phi sine theta, and cos phi. And then here is rs squared sine phi. Next step is to get vector field on the surface written in terms of phi and theta. Here I wrote f equals f of rs because we plugged in the radius of the sphere. R hat I wrote in terms of phi and theta here. And then you would need to perform the integration. The integral would look like this. Theta would be going from 0 to 2 pi. Phi would be going from 0 to pi. Then you have the vector field. Then you have this factor here. And then you have d phi d theta. Then you would plug in the expression for f, which I'm showing you here. This part is this thing I just showed you over here. And then you have d phi d theta, which is equal to this. If you would need to first, you would need to figure out what this dot product is. And if you work out all the math, you would find that this dot product with this is equal to 1. So then you take f of rs, you can take it out of the integral. You would get f of rs times integral 0 to 2 pi, integral 0 to pi, rs squared sine phi d phi d theta, and then you can proceed with integrating this. Now this part, if you've done the calculation before, you'll recognize that this is exactly the scalar surface element for the integration over the surface of the sphere. And this is sort of what we also did when we did the shortcut. We shown geometrically that r hat, which was the direction of f, and turns out it's, and it was also this part, dot product with ds, which was with the vector ds, which was this part, is equal to scalar ds, which we have here, and then we took out f of rs out of the integral, And we got this. And then we also before made use of the formula for the surface of the sphere, which is 4 pi rs squared. Whereas in the full derivation, you would need to integrate everything. One thing I want to mention is that we won't always be writing rs, and I think in the reading assignment you've already seen it as being written as just r. So depending on the context, r would mean either the spherical coordinate variable that can change. This would be for volume integration of some charge density, or it could mean some fixed radius of some Gaussian surface. So this is all for the left-hand side of the divergence theorem, and the variability of the problem comes in what the charge density looks like. So there are several things you can encounter. One would be continuous charge distributions. For example, uniform charge distribution over some shell. So it would look something like this. You could also have shells of 0 thickness of whatever radius, say r. Expressions for such a shell would be theta delta of r minus the radius of the shell, and it's measured in coulombs per meter cubed, just as any other charge density. Now, sigma, which is the surface charge density, would be measured in coulombs per meter squared, because it's the amount of charge per unit surface of the shell. You can also find point charges. Those would come in two different forms. One is the spherical expression, which is q over 2 pi r squared delta of r, again coulombs per meter cubed. Oh, and I forgot to draw the point charge. The other expression would be q delta of x, delta y, delta z, also in coulombs per meter cubed. And this q here is the charge of this point charge, and is measured in coulombs. Now let's do problem 7 from section 3.5 of assignment 5. In this problem, you're given this spherical geometry where you have point charge q in the middle, right here. You have the first spherical shell with uniform volume charge density ρ2, shown here, and you have a second spherical shell with 0 thickness, this shell right here, with surface charge density sigma 3, labeled here, and the radius r3. The first calculation part of this problem asks you to get the expression for ρ1, which is the charge density of the point source, and the answer should be in spherical coordinates. This you can get from one of the tables in assignment 5. This would be q divided by 2 pi r squared delta of r, and this is measured in coulombs per meter cubed. You're also asked for ρ3, which is the charge density of the thin shell, this one, also in spherical coordinates. This would be sigma 3, this one, times delta of r minus the radius of the shell, which is r3. This is also coulombs per meter cubed. In the next part of the problem, you're told that f equals r hat at r equals r1 over 2. r1 over 2 is here because this is r1, this is half of that. So this is the field at this location. At r equals r2, which is this radius, the field is equal to 2r hat. Oh no. Is equal to 2r hat. And at r equals r3, just outside the shell, the field equals 0. So this would be somewhere here. And you're asked to compute rho 2 and sigma 3 as a function of different radii in the problem, and to give the units of rho 2 and sigma 3. Rho 2 is the charge density of the thicker shell, and sigma 3 is the surface charge density of the thin shell. To solve this problem, we will be using the divergence theorem. To use it, we need to first set up Gaussian surfaces, and we will set those up at the 3 radii where we're told the field. So the first surface would be at r1 over 2. This is here. The second surface would be at r2. And the third surface would be at r3 plus a little bit. Now this delta R3 is just some really, really small number. Just as long as it's non-zero, it's enough. Then we will simplify the left-hand side and the right-hand side of this expression. For the left-hand side, we would assume that f equals to f of r times r hat. Then we would plug it into the expression for the integral, which I did here. This f of rs is a constant, so it comes out of the integral. And then you're left with f of rs times the surface area of the sphere. Then we would evaluate this for the 3 different surfaces by plugging in what rs equals to. So the first surface has rs equal to r1 over 2. It's this one. This is r2, this one. And the third surface is r3 plus delta r3. Now you will notice that here I wrote r3 instead of r3 plus delta r3. This is because this part is for evaluating the surface area of the sphere, and this surface area doesn't really care if this is just outside the cylinder or it's right here. So for this part of the calculation, R3 is fine. You don't need to add delta R3. Now let's write what this is. F at R1 over 2, which is the radial component at this location, is equal to 1. You can see right here because F equals to R hat. This would be 1. F at R2 is equal to 2 right here. And f at R3 plus a little bit, which would be just outside the shell, is equal to 0. Now let's get the expression for the right-hand side of divergence theorem for each of these 3 surfaces. The first surface at R1 over 2, which is this red surface here, is going to give us this. It's the integral of rho dv, like this, in spherical coordinates. Very important, the Jacobian for spherical coordinate integration. our theta is going to go from 0 to 2 pi. Pi is going to go from 0 to pi. R is going to go from 0 to this radius, R1 over 2. For rho, we plug in the expression that we got in part B. This was Q divided by 2 pi r squared times delta of R. Then we perform the integration. This constant Q over 2 pi comes out of the integral. Next, you have integration from 0 to 2 pi of things that don't depend on theta. So then we get, we get 2 pi here. Then we have integration of sine phi from 0 to pi. And then we have integration of, sorry, there is a mistake. No, there is no mistake. Okay, then we have integration of things that depend on r, but this r squared cancels, so we're left with delta of r, which is here, and then dr. Then what we have here is this. We have this integration. I'll just do it on the side. I might sometimes skip this step because it's really common integration. So this sine phi d phi equals to cosine phi with a negative from 0 to pi. This is the same as cosine pi minus 0 and then negative cosine of 0 then with a negative sign, but we can flip the bounds and flip the sign at the same time, so we'll get cosine of 0 minus cosine of pi, which is equal to 1 minus negative 1 equal to 2. So this guy is 2. This one, remember how we're integrating half of the delta peak if we're integrating from 0? So this integration is going to give us 1/2. Then we have this 2 pi cancels with this 2 pi. This 2 cancels with this 2. And then we are left with just Q. That's all we have. So this is the total charge enclosed in this first Gaussian surface. Now, we could have gotten the same answer just by looking at the givens, because we were told that there is a point charge of value Q right here. So we actually just physically know that this is supposed to be Q. For the second surface, we do the same kind of integration of rho, but there is a difference. In the first Gaussian surface, there was only one kind of charge, which was this Q. In this green surface, there is two kinds of charges. There is this Q here, and there is this uniform shell. That is why I wrote Q, which I add to the calculation of the charge of this uniform shell. For the uniform shell, this integral setup is the same as before. This is the Jacobian. These are the limits on phi and theta. R, it's really important. Very common mistake. It's so common that I made it in the first version of this recording of this video. So R, you would think it goes from 0 to R2. Sure, that's true, but actually it's supposed to get the correct answer, if you're putting rho 2 here, which remember was this uniform charge density value, then these bounds should go from R1 to R2. The reason why is this. You can write integral from 0 to 2 pi, 0 to pi, and then 0 to R2, and then here you would write some sort of expression for the charge density of the uniform shell. And the correct expression would be something like this. Well, I'm kind of abusing notation here because it's not very clear, but I'll explain what I mean. If you want to write it from 0 to R2, you have to write here instead of row 2, you would have to write row 2 for R that is between R1 and R2. And then 0 otherwise. But then this is sort of complicated. This actually immediately reduces to this. Because you have this bound is the same, but this bound takes into account the fact that the charge density is 0 between r equals 0 to r equals to r1. Okay, let's perform the integration. We have q plus rho 2, which comes out of the integral. Then we have integral over theta, which gives us 2 pi. We have integral over phi. The only thing that depends on phi is here, which I put here. And then we have 0 to r2 of r squared dr. This integral is equal to 2, we just found on the previous page. This integral, sorry, there is a mistake actually. Just going to erase this. This should be r1. And this would be r cubed over 3 from r1 to r2. This is equal to r2 cubed minus r1 cubed divided by 3. Let's put everything together. We have q plus rho 2 times 2 pi times 2 and times rho 2 cubed minus r1 cubed divided by 3. Let's actually simplify this further. We get q plus 4 pi over 3. So 4/3 pi r2 cubed minus r1 cubed times rho 2. Now let's move on to the next surface and what's enclosed, which is this purple surface. There is 3 objects enclosed inside. It's the point charge, the uniform shell, and the thin shell. So we need to include Q. We need to include the charge of the uniform shell, which we just calculated. And then we need to compute the charge of the thin shell. Here again, we have this volume integration. This is the Jacobian. These are the bounds on phi and theta. The charge density that we need to put here is sigma 3 delta of r minus r3. This is the charge density of the thin shell. The bounds on r will go from 0 to r3 plus a little bit. Now it's really important in this case that we add this part, because if we integrate up to here or up to the middle of this thin shell, we would get incorrect result for the charge enclosed, because here this surface wouldn't enclose the charge of the thin shell at all. Here I copied these 2 charges. Then I have this plus sigma 3, which came out of the integral. We have this integration over theta giving 2 pi. This integration over phi only takes this sine phi. Integration over r is going to include this delta and then this r squared and dr. Then we are computing this is going to be sigma 3 times 2 pi times 2. Now for this part, we are going to use what's called sifting property of the delta function or sampling property of the delta function. We know that this delta peaks at the value r equals to r3. And this integration goes from 0 to r3 plus a little bit. So the integration interval captures this peak. And when this happens, delta will sample out the value of the function that multiplies it. So we're going to get the value of this r squared at the location of the peak, which is going to be r3 squared. Or we can simplify it as 4 pi r3 squared. Now there is a second way to get this same result is by using the physical meaning of this sigma here. We know that sigma 3 is the surface charge density, so it's the amount of charge per unit area of the surface. So to get the total charge of this thin shell, we want to take this surface charge density and multiply it by the area of the surface of the thin shell, which is going to be sigma 3 times 4 pi r3 squared. So this is it for the right-hand side of the divergence theorem. Now let's equate the left-hand side of the divergence theorem to the right-hand side to solve for the two unknowns that we have. Here I wrote out all the left-hand sides. These are all the right-hand sides. Let me explain. This first one is for the red surface. The second one is for the green surface. You can see this by observing that it has a 2 for the radial field component, and it has two different charge densities here, like two different charges. And third one has three different charges, and this is the one for the purple surface. Our unknowns are rho 2 and sigma 3, and we want them in terms of just the radii. So let's use this second equation to get rho 2. You get an expression like this. Let me explain. What I did here is I took this. I subtracted this, which was q. You see this, I plugged it in. Let me highlight this as well. This q I subtracted here, and I plugged it in from here. And then I divided everything by this. So this is what goes in the denominator. Okay, so rho 2 is now known. Now let's solve for sigma 3. This last equation has sigma 3 and then two values that are already known because q is solved for and rho 2 is solved for. So let's write sigma 3, what it is. We have, what I did is this, I took this part, I transferred it to the left-hand side. Sorry, this should be 3. Okay, I'm going to fix it in the main notes later. Okay, these are supposed to be 3. So this is it. Then I divided everything by this 4 pi r3 squared. By the way, this part is just 0. So I divided it by this. This minus sign came from the fact that we shifted everything to the left-hand side. Okay, now what we can do is we can take the first equation, plug it in for q, and take this and plug it in for rho 2 and simplify things. But there is a little shortcut you can use. You can realize that in the second expression, we have already q plus 4 over 3 pi rho 2 cubed minus rho 1 cubed times rho 2. And we know that this is equal to 8 pi r2 squared. So you can just take this and replace it with 8 pi rho 2 squared right here and copy this down here. Let me put an arrow so you know what I plugged in where. So I took this and I plugged this into this numerator. That's how I got this. Okay, so we found all the unknowns. There's two things left, is to simplify, and we were also asked for the units. And by the way, it's a good idea to always just write the units, even if we didn't ask for them. Okay, let's simplify things. For row 2, you have this 2, it's squared, it cancels with 4. You have 3 that goes to the numerator, and pi cancels, so you're left with 3 over 4. Then we have 8 r2 squared minus r1 squared. And in the denominator, we have r2 cubed minus r1 cubed. The units for row 2, remember it was the charge density, and it's measured in coulombs per unit volume. For sigma 3, pi cancels. We have 8 over 4, and then we have r2 squared and r3 squared. So then we get negative 2 r2 squared over r3 squared. The units for sigma 3, which is surface charge density, is coulombs per unit surface area. Okay, that's it for this problem. Now let's do problem 10 from section 3.5 in assignment 5. You are given a spherical shell with charge density equal to negative r. Right here, it's negative r between r1 and r2, this and this radius. And you are also told that there is a superimposed field E, 0, 0, A everywhere in space. Let me draw that field in orange. It would go something like this. This is E. Now, if A was negative, then it would go down instead. And we don't know the sign just yet. You're also told that the total field, when you add the field produced by the shell, let me label this field F, produced by the shell, if you add the superimposed field to it, you get 0 in total. So I'll use blue for the total field. And sorry, you don't get 0 in total. You get 0 in total at this point, 0, 0, 2, R2. So it's going to be here, 0, 0, 2, R2. At this point, F equals 0. And actually, it's not equal to 0 at other points. I made a mistake, sorry. Okay, and the goal is to find this constant A over here. Now, I really want to emphasize that this problem is not symmetric because you started off with a symmetric problem when you just had the shell. This shell produced the field something like this. It's radially, well, it's spherically symmetric. By the way, I'm drawing this the arrows inwards because the charge is negative. So this was F, but the total field is actually quite messy. And by the way, this should be F total. The total field, well, is equal to 0 here. At this point, if you imagine adding the two arrows, you would get probably something like this. Here, you would get something that's sort of upwards and sort of to the right, so something like this. Here, you get a strong field, that's superimposed like this. So you really see this whole problem loses symmetry completely. So it's something quite strange. And now if you attempt using divergence theorem for this overall problem directly, you'll either be stuck because you wouldn't be able to simplify the integrals, or you will get nonsense results if you end up using simplifications that you're not supposed to use. So the answer to to solve this question, a way to do it is to use superposition. First, we would want to find the field due to this shell at this point. So let's do that. We would want to set up a Gaussian surface that will pass through the point where we're interested in finding the field. Let's do that. So our surface is going to be a sphere of radius 2r2. Let me actually draw this here because it looks nicer. This would be the Gaussian surface. Then we would evaluate the left-hand side of the divergence theorem. Again, we're assuming that f has a radial component and then r hat. So we get something like this. Again, this calculation we did already several times. So I'm showing the result. We have the radial component of f times the surface area. Okay, I'm going to use black for this. The surface area of the Gaussian surface. Area of the Gaussian surface S. And this is the radial component of f. Okay, so this is the left-hand side. Now the right-hand side, we'll have this integration of rho. Theta is going to go from 0 to 2 pi. Sorry. Pi is going to go from 0 to pi. Here I wrote the expression for rho only inside this shell, so the integration should go from r1 to r2. Remember the discussion about not putting 0 here if you didn't consider this being 0 here. Okay, so we have this. Now let's integrate over theta. This is going to give us 2 pi. This minus over here came from here. Then we have the integral over phi, which is integrating this. And now what we're left with is the integral over r. Then we have r cubed, and this minus we already took it out. And the integral is from r1 to r2. This integration gives us the following. This is equal to 2. We already did this calculation. This is equal to r to the 4 divided by 4 from r1 to r2. So we get negative 4 pi times, so this gives 4 pi times a fraction over 4, and here we have r2 squared, sorry, r2 to the 4, oops, minus r1 to the 4. And these 4 and 4 cancels. Now let's equate the left-hand side and the right-hand side and then get the field f at this point. Here I copied this expression. Here I copied what I got from this calculation. Then solving for radial component of the field at radius 2r2, we get the following. We have this was on the right hand side. This was the denominator. This 4 is here, and then this 2, it's squared, so we get a 4. And this is equal to negative. We have pi canceling, so we get our 2 to the 4 minus our 1 to the 4, and this is all divided by 16 r2 squared. So this gives us radial component. Now let's get the actual vector field. Vector field at any r equals to 2r2, so everywhere on this red surface is equal to this, where I took this radial component and then added the direction to it. Now let's use this field that we found for this red Gaussian surface to get the field at 0, 0, 2, r2. And we want that field written in Cartesian coordinates because we want to add it to this Cartesian E. So let's do that. Here I copied the field, and you can see that at this observation point, we have our hat going upwards like this, and this is equal to z hat at this point. So f, one second, f at the point 0, 0, 2, r2 is equal to negative r2 to the power of 4 minus r1 to the power of 4 divided by 16 r2 to the power of 2, and then instead of r hat, we would write z hat. This way, at point 0, 0, 2, r2, we have E, which is shown in orange, being A times z hat. F is equal to this expression we just found here. Then we add the two fields together for this point, and we are supposed to get 0. This lets us find A. We know that the only way for this expression to be 0 is if A is equal to this constant. So that's all we need to do for this problem.